Welcome to the second session of the sheet 5, where we are going to evaluate the steady state, where we are going to evaluate the range of the R value for the control system stability, a problem related to the load frequency control. In the last class, we have dealt with the problems related to the closed loop transfer function, route service criteria, and also range of K for identifying the stability of a control system. Identifying the stability of the control system is something related to this problem. We have utilized the method called route service criteria for the evaluation of the range of K under stable conditions. It is also a similar problem, problem number 4, where we need to evaluate the range of the R value for a given system whose turbine time constant tau t is equal to 0.5 seconds, governor time constant tau g is equal to 0.2 seconds, generator inertia constant tau h is 4 seconds, and whereas this is the R value for which we need to evaluate the range. This is the R for which we need to evaluate the range. Load varies by 0.8% for a 1% change in frequency, that is 8 D value is equal to 0.8. It has to be evaluated for a corresponding steady state error for unit ramp input. The input is of the form unit ramp. To start with, this is the given information. We need to evaluate. This is the single line diagram, block diagram of the load frequency control system. Substitute the value of H, tau g, tau t. H value, it is given in the problem for a given, see it here, H is equal to 5 seconds. Substitute the value of H. D value is given 0.08 or 0.8. Substitute that value 0.8, and S value, here tau g value is 0.2 and tau t value is 0.5. This forms your block diagram representation of the given problem. The input is the load change, and there will be a change in frequency. And 1 by R, the range of this R has to be evaluated. For this, let us evaluate the characteristic equation. Characteristic equation is 1 plus G of S into H of S. This is G of S and this is the H of S. 1 plus 1 by R divided by G of S into H of S is 1 by 10 plus 0.8, 10s plus 10s, 2s, 2 into 5 into s, 10s plus 0.8. This should be equal to 0. So the complete transformation, multiply this with this, divided by, you will get the denominator, shift this denominator to this, and you will get it as 1 plus 0.2s into 1 plus 0.5s, 0.8 plus 10s plus k is equal to 0. If you simplify this, you will get this parameter into 0.8 plus 10s plus k is equal to 0. Again simplify this, multiply this, you get it as 0.8 plus 0.56s plus 0.08s square plus 10s plus 7s square plus s cube plus k. If you write in the order of the s value, s cube plus 7.08 s square plus 10.56 s plus 0.8 plus k is equal to 0. This is the final expression. We need to evaluate the range of this k value. We need to evaluate the range of this k value for this stable system. So let us use the routes table. If we use the routes table, coefficient of to start with s cube, s square, s power 1, s power 0, and then coefficient of s cube 1, alternate parameter 10.56. Then we have coefficient of s square 7.08, alternate parameter is 0.8 plus k. And then s power 1 will be equal to 7.08 into s power 1 will be equal to 7.08 into 10.56 minus 0.8 plus k into 1 divided by 7.08. So what are we going to get? 7.08 10.56 is 74.56 minus 0.8 plus k divided by 7.08. Onto the whole, you will get it as this value completely can be written as 7.96 minus k divided by 7.08. And this parameter is equal to 0.8 plus k. Here we don't have, hence it becomes 0, minus we don't have any parameter. This parameter will become 0 divided by 0.8 plus k. You will get 0. And coming to this parameter, this into this 73.96 minus k divided by 7.08 into 0.8 plus k minus 0 value divided by 73.96 minus k divided by 7.08, you will get it as 0.8 plus k. We are getting the same parameter which is present in the constant. Okay, it means our calculation is right. Now for a stable operating system, there should not be a sign change. This is positive, this is positive. The first parameter should be positive. Now in this case, positive, it means this parameter should also be positive and this parameter should also be positive. It means one value is 73.96 minus k minus 0.708 should be greater than 0. This is 1, and already there is no negative parameter here. It means this should be positive. So you can write it as 73.96 minus k divided by 7.08 is greater than 0. Simply we can write it as k should be greater than 73.96. K should be greater than 73.96. Whereas we want the evaluation of r. R is k can be written as k is equal to 1 by r. In place of k, just we will write it as 1 by r. So r will be greater than 1 by 76.96. So r should be greater than 0.013159. This forms your solution. This forms your range of k. It means r should be greater than this. Coming to the second part, we need to evaluate the change in frequency, change in steady state frequency. Change in steady state frequency, delta omega ss is equal to minus delta pl into 1 by d plus 1 by r. Substitute the value of change in load minus 0.2, which is given in the problem. Change in load is given as, see, there is a change if change in load is 50 hertz and the rated value is 250. Sorry, change in load is 50 megawatts and the rated value is 250 megawatts. So the change in load in per unit value will be, this is in per unit value. How we got 50 divided by 250? 50 divided by 250, you will get it as 0.2 minus 50 divided by 250 is 0.2 into 1 divided by d value is 0.8 plus 1 by r value is given as 0.05. You will get it as delta omega ss is equal to minus 0.2 divided by 20.8, which is equal to minus 0.0096 per unit value. If you want to represent this per unit value in hertz, this value per unit value in hertz, multiply this value into f and divided by 2 pi. This is 60 F is fundamental frequency 60 divided by 2 pi, you will get it as minus 0.0916 Hertz. Then the steady state error ESS is equal to minus delta PL d by d plus 1 by R. Compare these two values. If you write d, it will become steady state error. It means minus delta P by L divided by d plus 1 by R is delta omega SS into d. D value is already given, delta omega SS into d. Delta omega SS, we got it as minus 0.0096 per unit value into d value is 0.8. It is given in the problem. You will get it as 7.68 into 10 to the power of minus 3 per unit. This forms your steady state error. With this, problem number 4 is completed, related to the automatic load frequency control. Coming to the automatic voltage regulator, problem number 5. The given system, this is the steady state frequency delta omega SS, which has been evaluated, and steady state error is evaluated in the second part. Just we need to substitute the value in the given formulas. Now coming to the problem number 5, the AVR of this generator has the following parameters: KA, KE, KG, KR are given. The gains of the KA, KE, KG, KR are given. KA is not yet given. We need to evaluate this. And TA value, time constant of the amplifier, time constant of the exciter, time constant of the generator, and also the sensor. These are the values. We need to evaluate the range of KA, Route's method, Route's table, using Route's table, this VSS and also ESS. Let us evaluate this. This is the block diagram for an automatic voltage regulator. Simply, what is the common thing we have? K divided by 1 plus ST. This is the order of the system. This is the transfer function of the amplifier, transfer function of the exciter, transfer function of the generator, and also the transfer function of the sensor. Now, substitute the values of KA. Sorry, KA is not given. We need to evaluate this. Substitute the value of TA, KE, TE, KG, tau G, KR, and TR. Whatever values have been given, just substitute the value and evaluate the characteristic equation. Tau A, KG, tau G, and then we have KE, tau E, KE, tau E, KG, tau G, and the sensor values. So after substitution, it is given in this tabular column. From these values, after substitution in this block diagram, we will get this block diagram. Now, for evaluation of the KA, we need to form the transfer of our characteristic equation. 1 plus GH, 1 plus G of S into H of S is equal to 0. G of S value is product of these three, and H of S value is this parameter. KA divided by 1 plus 0.1 S, 1 plus 0.4 S, 1 plus S into 1 by 1 plus 0.05 S. 1 plus KA, when you evaluate this, you will get it as KA divided by 1 plus S by S of 10, 1 plus S by 2.5, and it means I am writing this in the simplest form. 0.1 S can be written as 1 S by 1 by 10, 0.1 can be written as 1 by 10, 0.4 can be written as 1 by 2.5, and it is already there. What we want S parameter should be coefficient of 1, should be alone. So I am writing it as S by 10, S by 2.5, S as it is, and 0.05 S can be written as S by 20, and this complete thing can be written as denominator 10 plus S, 2.5 plus S divided by 2.5, 1 plus S already there, 20 plus S by 20. You will get this equation, and then 1 plus 500 KA divided by 10 plus S into 2.5 plus S into 1 plus S into 20 plus S. When you evaluate this, you will get it as 10S plus 2.5 plus S, and 1 plus S plus 20 plus S plus 500 KA is equal to 0. This forms your characteristic equation. Once we get this, let us separate them. Once we get this, when we separate product of these two, we will get this value, product of these two, we will get this value. Again, product of these two expressions, we will get it as this lengthy value. And then when we write this in an order of s, in the order of s, we will get s power 4, s cube, s square, s power 1 and s power 0. And let us put this in the form of Raoult's table. When we substitute this in the form of Raoult's table, s power 4, s cube, s square, s power 1, s power 0, we will get it as 1 into 7. See, s power 4, this parameter coefficient of s power 4 is 1, alternate 1, coefficient of s square 307.5, then coefficient of the alternate one is 500 plus 500 Ka. Come to start with s cube 33.5, then 775, then after that we don't have anything below this, so we will write it as 0. Then we have s square. S square parameter can be evaluated as 33.5 into 307.5 minus 777. You will get it as 284.386. Sorry, this divided by 33.5. This into this 33.5 into 307.5 minus 775 into 1 divided by 33.5. You will get it as 284.365. And to write this parameter, this into 777 into 500 plus 500 Ka minus 0 into this parameter 0 divided by 775, you will get it as this parameter. To write this value, this into 0, sorry, this into 775 minus this into this divided by 284.365. You will get it as 716.1 minus 589. Ka. This value. Now if you want to write this value, 500 Ka into 0 minus 0 into 775 divided by 500 Ka, you will get 0. Now to write this value, this into this minus 0 into this divided by 716.1 minus 58.9 Ka. You will get it as 500 plus 500 Ka. This and this expression are same, hence our evaluation is right. Now for a stable system, all these should be of the same sign. If this is positive, this should be positive, this should be positive. It means this should be positive and it is already positive. If Ka is positive, this expression is also positive. Hence this value should be positive. For making this value positive, 716.1, 589 should be greater than 0. So Ka should be less than 716.1 divided by 589.9. So Ka should be less than 12.16. So Ka should be less than 12.16. Now this is the range of Ka. Coming to the steady state response. So limit h tends to 0, s of Vt. This is the where V of t is the closed loop transfer function. V of t closed loop transfer function. To evaluate this V of t of s is equal to G by 1 plus G of s divided by 1 plus G of s into h of s. G value K into 10 into 2.5 from where? From this. From this, the product of these three is your G. Okay, this is G and this is H. So G of s divided by G of s into H of s. 1 plus G of s into H of s. Where we got 1 plus G of s into H of s? Here. See, 1 plus G of s into H of s. Or simply you can write it as 1 plus G of s of H of s is equal to this. This complete expression we are writing it here. Now from this denominator part and this denominator part can be eliminated. 20 of s will be moving to the numerator. You will get this expression. And to evaluate this for the step input, delta VSS steady state response is equal to limit s tends to 0, s of V of t into V of t of s divided by s. This s gets cancelled. You will get it as limit s tends to 0, Vt of s, we got this value, substitute this value. In this, if we substitute s tends to 0, this parameter 25 into 20 into kA divided by 500 plus 500 kA. From this parameter will become 0, so we will get it as 500 divided by 500 plus 500 kA. This 500, this 500, this 500 will be cancelled. You will get it as kA divided by 1 plus kA. This forms your steady state response. Coming to the steady state error for the step input, steady state error is equal to limit s tends to 0, s of r s divided by 1 plus g of s into h of s. Limit s tends to 0, s into r of s value is 1 by s, 10 plus s into 2.5, this is 1 plus g of s into h of s, which has been evaluated here, which we got it this value. Just substitute this value. Okay. Limit s tends to 0, s into r of s divided by 1 plus g of s into h of s, s into 1 by s. R of s value step input is 1 by s. This s gets cancelled, and this is 1 plus g of s into h of s. Substitute the value of s is equal to 0. You will get it as 500 divided by 500 plus 500 kA, and here 500 after cancellation you will get 1 by 1 plus kA. This completes your sheet 5. This is the problem related to the load frequency, automatic voltage regulation. In today's session we have finished the problems related to the load frequency control and automatic voltage regulator. With this we have completed the sheet 5. If you are having any doubts, please ask.